Analyzing our value stream, we identify a number of constraints that limit its effective capacity. The most visible constraints are the capacity of the different steps, but there are other not so obvious constraints, such as the capacity variation of some of the steps. Process simulation helps us understand the value stream dynamic behavior, how variation affects key process metrics, such as work in process, lead time, throughput, cycle time, on-time delivery, etc. Understanding these dynamic effects will enable us to get to the root cause of problems, implementing definite solutions and not just containing the symptoms. Download this Excel simulator onto your PC from OneDrive. Let us now review some process flow concepts. Throughput is a measure of speed. It is the number of items actually processed per unit of time. Cycle time is the time elapsed between two consecutive outputs. Takt time is the cycle time required by the customer or market demand. WIP, or work in process, is the number of items being processed or waiting to be processed in the system. Lead time is the total time in the system, that is, process time plus waiting. All these concepts can be applied to a single workstation or to the whole value stream. This basic model illustrates the concepts we have just seen. Let us now apply this matrix to a car assembly line. The time from starting a new car until it goes out of the line is typically 25 hours. This is the lead time. It includes process times and waiting times. A car is finished every 2 minutes. This is the cycle time. If it is the cycle demanded by the market, it is called takt time. This takt of 2 minutes is equivalent to 30 cars per hour, which is the throughput. Once a line has reached stability, we can apply one of the most basic process laws, Little's law, which is the process equivalent of speed equal to distance divided by time. If we replace speed by throughput, the speed at which items are processed, distance by work in process, total number of items in the system, and time by lead time, time to process an item, we obtain Little's law, which is throughput equal to WIP divided by lead time. In this process, lead time is the time from one item coming in until it goes out. The rhythm at which items are coming out is throughput. Work in process is the number of items either waiting or being processed. Here we apply Little's law to a service case. Someone joining the queue wants to know how long it will be before he gets serviced. If there are 26 people in the queue, that is WIP equal to 26, and 2 persons get serviced per minute, that is throughput equal to 2 per minute, lead time will be equal to WIP divided by throughput, that is 26 divided by 2, which is 13 minutes. So his lead time will be 13 minutes. Now we will apply Little's law to a previous example of the car assembly line. We want to know how many cars are in the process. So therefore, we want to calculate WIP as a function of throughput and lead time. Since throughput in our case was 30 cars per hour, and lead time was 25 hours, we multiply, and that gives us 750 cars in the process. So that will be the number of cars in the whole line. In this four-step process example, each step takes 10 minutes. Therefore, total lead time from start to finish will be 40 minutes. WIP is 4 units, one being processed on each step. Every 10 minutes, one unit is finished. This is the takt time. Throughput, number of units per hour, will be the inverse of takt, that is 6 units per hour. In this example, the curve on the left represents the cumulative number of items started in the line. The curve on the right is the cumulative number of units finished. From hour 0 to 25, the process is stable. The start line is parallel to the finishes. The horizontal distance between these two lines represents the lead time, time elapsed between one item being started and being finished. The vertical distance between the two lines represents the work in process, number of items in the system in that moment in time. We assume that each item being started has to wait its turn in a queue until all the items which are already in the system are processed at the throughput rate. The total time in the system for each item will be, therefore, the time to process all the items in the system, including itself. From hour 25 to 30, we have decided to stop all starts in the line. As a result, the WIP has been depleted from 20 units, it has gone down to 10. And therefore, we see that the lead time has also been halved from 10 hours to 5 hours. From hour 30 onward, the line is also stable. The throughput of the line in this chart is the slope of the finish line. Its value is 2 items per hour. We can see that the slope has remained constant all the time. Therefore, lead time varies proportionally to WIP. Lead time is equal to WIP divided by 2. Just-in-time can be achieved by limiting artificially the output buffer capacity to a minimum in such a way that nobody is allowed to process an item unless he has room for it in the output buffer. This empty space is created when the next workstation removes an item from the buffer. If we follow the same procedure up to the end of the line, we see that it is the final customer who activates the whole line by removing finished product or service from the end of the line. This hole created by the customer bubbles upstream along the whole line, activating as it goes along all the workstations. This mode of operation is called pull system as opposed to push system, where the items are pushed into the line and they are processed as they come, in case of no buffer constraints. Capacity utilization is the rate between customer commitment and line capacity. In some processes, not all the items which start in the line find their way to the end. Some are lost on the way. This is something common in state-of-the-art technology lines. Some items are found defective and non-recoverable, and therefore they are discarded along the way. This effect is also common in business processes. Every time there is a control, a signature, etc., there is a possibility of a unit being rejected and therefore not proceeding any further in the process. An example of this is a purchase order which is rejected by the finance department due to budget restrictions. The immediate consequence of yield loss is that since there are more items starting the line than items finishing, The capacity requirements in our workstations will not be constant along the line. The first workstations require more capacity than the last. Compound yield is the overall yield resulting from all step yields. These are some examples of batch mode operation. A remote process step, items accumulated to fill a lorry. Reporting at the end of the shift. Check incident log only once in the shift. We will now use the three-step process simulator in Excel that you have just downloaded. Yellow numbers are the process inputs you can change. You can see their description, default values, and limits by placing the cursor on each one. These are the control buttons of the simulator. You can just press them or use Control plus the initial letter. In the bottom graph, you can see the evolution of total lead time, and in red, every time there is a commitment to the final customer. We are now going to run a number of exercises with the simulator. The first one will be the ideal process. So press Start just now to run the simulator with the default values. You have committed to deliver to your customer exactly 100 items each day. He absolutely needs each one of them. One missing item can cause him a major disruption. Therefore, if one single item is missing, it will be considered as a decommitment. Each item has to be acted upon by 3 different departments in sequence before being delivered to the customer. At the beginning of each day, there are 100 items in process on each department, and each department is processing 100 items. Therefore, the customer gets at the end of the day the 100 items you have committed. Everything is so perfect that nothing seems to move. If it was not for the clock counting the days at the top right corner of the screen, one would think that the simulator has stopped. Now we will answer some questions. How is the delivery performance? We see that the percentage on time is 100. Average WIP, we see the average WIP is also 100. Average lead time is 1. So this is the ideal situation in this process, and we will use it as reference for future exercises. In the ideal case seen before, all departments had a capacity to process 100 items per day, and that is exactly what they did. In real life, this perfect matching of the capacities of the different departments does not happen. There will always be differences in the capacities, even if theoretically they ought to be equal. If these capacities are different, there will be one department which will have the lowest capacity of the whole line, and this department will constitute a bottleneck for the total process. We will call this a capacity bottleneck. To distinguish it from other possible types of bottlenecks, we will see later. The capacity bottleneck may be due to some critical equipment, oven, tester, etc., which is in short supply. The cause may be a critical skill, which is in short supply in the organization. It could be a person who is ill in one of the departments, or an authorization which only one person can sign and happens to be very busy. We will now simulate a capacity bottleneck in step 2. To do that, we press stop to stop the simulation, then change step 2 capacity to 99 and press enter. Then press the start button. Now run the simulator for a few minutes and then answer these questions. What happened to delivery performance? What is the proportion on time? Where is the queue building up? How is lead time affected? What is the average lead time? Why? The first priority is customer satisfaction. How can we improve delivery performance if the bottleneck cannot be improved? How about renegotiating the delivery commitment with the customer? In a normal situation, it is possible to compensate for a lower capacity in one department by working a bit faster in order to catch up with the work or by working overtime, etc. There are, on the other hand, some cases where there is a physical limitation which cannot be compensated by overtime, or there are legal constraints, etc., which prevent it. In a case like this, where there is no possibility to open up the bottleneck, all that is left to do is tell the customer and renegotiate with him volumes which are in line with the bottleneck capacity. We are continuing from the previous exercise, so now we press the stop button, change commit to 99 and press enter, and press the start button again. Now run the simulator for a few minutes and then answer these questions. How is the delivery performance now? Percentage on time? Is the queue still growing? What is happening to lead time, average lead time? Why? How can you stop the queue from growing further? How about limiting the line starts to the bottleneck capacity? The bottleneck is therefore dictating how much you can commit to your customer, but it also dictates how many items you should start at the beginning of the line. Starting more than the bottleneck can handle is a waste. The number of units coming out of the line throughput will be equal to the bottleneck capacity, and therefore all the units started above that capacity will simply pile up in front of the bottleneck, increasing not only the inventory but also the lead time. Continuing from the previous exercise, just press Halt to stop simulation, change step 1 capacity to 99, and press Start to simulate again for a few minutes. Now answer these questions. Is the queue still growing? What about lead time? What is the average lead time? Why? Why do we still have a queue if the problem has been solved? How can we reduce the queue? How about limiting starts below delivery level for some time? By controlling both the output and the input to the line based on the bottleneck capacity, we can now say that the problem is solved. But is it really? We see that the lead time is still too long, and this is due to the excess inventory which has accumulated in front of the bottleneck. Something similar happens when we have been overeating during holidays. Going back to normal eating habits is just not enough if we want to get rid of the extra kilos. In this case, therefore, we have to flush away the excess inventory, and one way we can do it by limiting starts below the throughput level until the excess is depleted. To deplete the excess inventory, we will now change step 1 capacity to 90. We press Start until the excess inventory is depleted, and then press Stop. Then we change back step 1 capacity to 99 and press Start. Now we can say the problem is solved, always with the restriction of the bottleneck capacity. Let us now answer a few questions. What happened to average WIP when you limited starts below delivery? Why? What happened to average lead time? Why? Did you miss any deliveries during this operation? How can you reduce excess WIP otherwise? How about applying just in time? Another way to eliminate the excess inventory in the line is to apply just in time. This consists basically in banning the accumulation of inventory by the crew. The way to do that is to work in pull mode. You only produce if there is empty place to put your output. That empty place will only be created the moment the next step in the line removes an item from your output buffer. To do this, we will first fill the line with inventory. We stop simulation, reset to set all process parameters to their default values, set all capacities to 500, start the simulator and run for a few minutes. Then stop and set back all capacities to 100. Now that the line is full with excess inventory, we will apply just in time by limiting the WIP queues to a minimum. In this case, 200, which means that everybody stops until they have space available in their output buffer. In this way, since we are delivering to the customer, WIP will be depleted in the line starting from the back all the way to the front. So we set all max queues values to 200 and press start. So we have removed all the excess inventory and WIP has gone back to 100, lead time back to 1, and we did not miss any deliveries in the process. So this looks a better method than the previous one, in this case of no variability. Apart from the capacity bottleneck experienced before, there is another type of bottleneck which is generated by the fact that a department has high variability in its performance. Although very often both types of bottleneck will be combined in the same department or process step, we will isolate the pure variability bottleneck, same average capacity as the rest, in order to see its effect on the total process. Typical variability bottlenecks are checking or approval steps, where some items take very short, but some others may take much longer. Public services or services which are outside our control may typically show also high variability. Poor quality also generates variation because you have to repeat some operations on some of the items. Equipment failure or low performance can also cause variation. When several concurrent inputs are required for a certain process step, it will happen that they will not arrive at exactly the same time. Therefore, one may have to wait until the last one arrives. This is therefore another source of performance variation. To run this exercise, stop simulation, reset, clear WIP, set step 2 variation to 20. That means the capacity will vary at random between 80 and 120. And then start simulation. After running for a while, let us answer the following questions. What happened initially to delivery performance? What was percentage on time? What is the average production of step 2? Who is causing the problem in the line? Is he likely to admit it? Why? What is the average WIP? Where is the WIP building up? Is the delivery performance improving as WIP builds up? What is percentage on time at the end? Why? What happened to average lead time? What can we do to reduce lead time? How about applying just in time? We now continue with the setup of the previous exercise. We will stop simulation. Now set maximum queues in all steps to 200 and start again. After running for a while, let us answer the following questions. What is percentage on time? What is the average production of all steps? Which step is causing the problem to the whole line? Is it obvious if we just look at the average line? Has lead time improved by applying just in time? What is average lead time? Can lead time decrease and on-time delivery get worse? Would you recommend this solution? Why? What happens if you have high variability and apply just in time? In a case of high variability, how can you reduce lead time and still meet your commitments? How about reducing capacity utilization? Assuming we are not able to eliminate the root cause of the problem, which is variability in step 2, how can we meet our customer commitments and at the same time reduce lead time? We will try reducing capacity utilization, which means that we will not commit to our customers 100% of our capacity, but only 95%, leaving the 5% balance to compensate for the variability of step 2. So we now stop simulation, reset, clear WIP, set step 1 capacity to 95, set step 2 variation to 20, set commit to 95, and start simulation. After running for a while, let us answer the following questions. What is the percentage on time? What are the following values after stability? Average WIP, average lead time. What are the negative effects of this case? What is the effective throughput in the line? What is average throughput? Would you recommend this solution? With high variability, when capacity utilization approaches 100%, then lead time tends to infinity. The reason for this is that variability makes throughput to drop and items start accumulating, making the queues, and therefore lead time gets longer and longer. With low variability, you can get close to 100% utilization and still have a good lead time. Yield loss are items lost during the process. This loss may be due to defects that force to scrap an item, or it may be due to the item being rejected in one of the control or approval steps. These are some examples of yield loss. Defective silicon wafer scrap, scrap after test quality control step, losses in transport service, order cancellation, work permit application rejection. In those cases where there is a yield loss in several process steps, we want to know what the total yield will be in order to size our organization properly. A yield bottleneck is typically a control step where rejection of some items may take place. Let us now simulate a yield loss of 1% in step 2. To do that, we stop simulation, reset, clear WIP, set step 2 yield to 99, and start. Let us now answer these questions. What is the total throughput in the line? Average throughput. Is the lead time affected in this case? Average lead time. How many units do you start in the line on each period, and how many do you finish? Average of 1, average throughput. What happened to the difference between started and finished units in the case of capacity bottleneck, and in this case of a yield bottleneck? In a process where items are lost or rejected in several steps, we want to know what the total process yield will be as a function of the step yields. This is what we call compound yield. To simulate this, set all step yields to 90 and start simulation. Let us now answer these questions. What is the total yield in this line? Average throughput. Is it what you would expect? How do you calculate total yield from step yields? Is 90% step yield acceptable? What will happen with larger number of steps? What happens to the difference between the units started and those delivered? Continuing with your previous example of yield 90 in all steps, we now want to increase capacities to be able to meet our commitment to the customer of 100 units and have an average lead time of 1, and we want to be on time 100%. So calculate the minimum capacities required to achieve this. When transportation between two locations is involved, you accumulate WIP to fill a van lorry, and then the whole batch is moved. Batch operation means accumulating items for a number of periods and processing them all in one period. This simulation will assume that the average capacity of the batch operating step is still the same as the rest of the steps. Some batch mode examples are daily transport delivery, fill oven before cooking a batch, burning run with full chamber. A step with a batch period of 5 and average capacity of 100 will process no items during 4 of the periods and 500 items in one single period. The average will still be 100 per period. To simulate, stop simulation, reset, clear WIP, set step 2 batch to 5, and start simulation. Now answer these questions. Is the batching of step 2 affecting the throughput of the total process? What is the average throughput? Is it affecting on-time delivery? Percentage on time? What is the effect on WIP? Average WIP? How is lead time affected? Average lead time? Why? In real life, we will not find single effects as seen so far, but rather a combination of the different effects. When several effects coexist, we will not find a single optimal solution. Depending on the relative cost of capacity versus inventory lead time, the optimal solution will vary. Typically, increasing capacity drastically will solve the problem, but it will be an expensive solution. So now stop simulation, reset, clear whip, set yield 99 in all steps except one, set variation 10 in all steps except one. Decide on the capacities to meet the following objectives. Percentage on time 100, minimum average capacity, minimum lead time. So now let us analyze your solution. Resulting average capacity, resulting average lead time, percentage on time. In the capacity bottleneck, throughput drops and WIP accumulates in front of the bottleneck. This generates an increase in lead time. In the case of a variability bottleneck, there was an initial drop in throughput, but eventually it is recovered when WIP accumulates. So there is an increase in WIP, and this generates an increase in lead time. When we applied just in time to a case of variability, there was a drop in throughput because you don't allow WIP to accumulate, but WIP therefore is maintained and therefore lead time also. In the case of a yield bottleneck, there is a drop in throughput, like in the case of a capacity bottleneck, but the difference is that there is no accumulation of WIP because the items are lost, and therefore there is no increase in lead time. In the case of batching, the effect is the same as in a variability bottleneck. That is, throughput is not affected, but there is an increase in WIP and an increase in lead time. The difference is that this increase is limited. An instant picture of your value stream may not be enough to understand what is going on. Variation is like a virus which passes undetected unless you are aware and measure it. Waiting times may be caused by variation, in which case you will not be able to reduce them unless you attack the root cause of variation. Different types of constraints cause different effects, which need to be understood in order to improve them. Pushing product through the value stream above the bottleneck capacity will only increase WIP and lead time, but not throughput. Applying just-in-time to a high variability process is a formula for disaster.